Lone pairs and multiple bonds can affect bond angles. And when we think about our geometries, even though we have our tetrahedral geometry, which has a bond angle of 109.5, when we look at something like methane, CH4, we do find that we have this bond angle of 109.5. We look at ammonia, NH3 there in the middle, we find we have a bond angle of 107. And when we have water, we find we have a bond angle of 104.5. Why is this? Well, this isn't due in part to the fact that ammonia and water have lone pairs of electrons on them. And what happens is the lone pair of electrons, because they're not going out into space, they hover up near the central atom. They take up more room and they push the bonds closer together to each other, causing bond angles to shrink. Well, ammonia, we have a bond shrinkage of about 2.5 degrees. And when we go from ammonia to water, we see another decrease of about 2.5 degrees. And so while it's not a profound effect, lone pairs on central atoms have the effect of shrinking the bond angles of other attached atoms. Likewise, multiple bonds can have an effect on shape. A double bond or a triple bond involves a lot more electrons stuck between two atoms, resulting in a greater electron density in that double or triple bond area. As a result from that, because there's more negative charge in the same amount of area, other bonds react to it by giving an increased bond angle. For example, you can see in this molecule here, the chlorine carbon oxygen bond is 124.3 because the carbon and oxygen have a double bond between them. The chlorine-chlorine bond, that is Cl-CCl, is only 111.4, and this is because those single bonds are reacting to that double bond presence in the molecule there. Now, while lone pairs and multiple bonds affect bond angle, we have another thing we have to talk about which takes into account both geometry and Lewis structure, and that is bond polarity. Bond polarity can be thought of as a tug of war. Different elements have different electronegativities, as we saw when we talked about Lewis structures, but because they have different electronegativities, that means they have different strengths of pull. So we have to take into account this tug of war where things may be pulling at different strengths on the central atom, and sometimes that results in a polar molecule or a nonpolar molecule. In a nonpolar molecule, basically you have a stalemate. No one wins. It's like two twins playing tug of war with themselves. They're both equally strong, they're pulling equally hard, and canceling each other out. However, in a polar bond, there is a stronger side, which basically drags along the rest of the tug of war. It's more like having a 5-year-old playing tug of war with an adult. The adult's just going to drag that little 5-year-old wherever he wants to go. Well, polar bonds suck electrons towards them, and so what happens is that we get a distortion in the electron field around the molecule, resulting in a side that is partially positive and a side that's partially negative. If we look at carbon dioxide here, we see, yes, carbon and oxygen, that is a polar bond for sure, but because they're placed 180 degrees away from each other, because it's a linear molecule, they cancel each other out, so the electrons are distributed uniformly throughout the molecule. However, something like NH3, ammonia here, we've got 3 hydrogens attached to our blue nitrogen. We have a tug of war, but one side is missing a player, and so the result is the electrons all shuffle towards the side where the player is missing. And you can see here with HCl, NH3, CH3Cl, we have 3 polar molecules because either an atom is a lot more electronegative or we have a lone pair on it. We also have 2 nonpolar molecules because basically the central atom on these 2 nonpolar is being pulled equally by the surrounding atoms and thus canceling each other out.